Next, we're going to introduce the property of continuous time Fourier series. The first one is linearity. Given that we have two pairs of Fourier series, then the linear combination of the original signal in the time domain will correspond to same linear combination of the spectra in the frequency domain, and vice versa. The second property is symmetry. If we have a pair of Fourier series and given extra condition that the original signal in the time domain is real, then the spectrum will satisfy these two conditions. That is, the amplitude of the spectrum is an even function, while the phase spectrum is an odd function. The third property is called time shift. Still given a pair of Fourier series, if the original signal shifted in the time domain, then the corresponding frequency spectrum will have extra phase term. So we can summarize this property as signal shift in the time domain causes phase shift in the frequency domain. Very similar to the time shift is the frequency shift. That is, if we have this pair of Fourier series, the shift in the frequency domain, or the spectrum is shifted in the frequency domain, that will cause the phase shift in the original signal in time domain. They are very similar, and they actually in certain symmetric patterns in here, but pay attention to the direction of the shift. The next is an example how we can make use of the shift property, help us simplify the evaluation of spectrum. So here we ask you to calculate the spectrum of this rectangle signal. We already know that previously for this symmetric periodic rectangle signal, the corresponding spectrum is something like that. And if we replace the parameters using the specific numbers in here, then this is the spectrum of this given rectangle periodic signal. And we know that this is the time-shifted version of that rectangle signal. Then the spectrum must be a phase-shifted version of the original spectrum. So here we go. This is the spectrum of this time-shifted rectangle signal. So this property makes our evaluation much simpler. And that the next one is circular convolution property. So before we introduce the property, we need to understand what is circular convolution. Given that we have two signals, periodic continuous time signal x1 and x2, and we define the circular convolution as this integral. And you can verify that the period of the circular convolution is an, again, periodic signal with the same period of the original two signals. This is the definition of the circular convolution. The property of the circular convolution states that if we have circular convolution in the time domain, then correspondingly in the frequency domain, the spectrum of the resulting signal actually is the multiplication of the spectra of the original signals and then multiplied by the fundamental period t sub none. So this is the content of the circular convolution. Circular convolution in the time domain corresponds to multiplication in the frequency domain. The next is the differentiation property. Given that they are a pair of Fourier series, if we do the first derivative of the original signal in the time domain, then correspondingly the spectrum will be multiplied by an extra term shown in here. The next property is called Parseval law, which is based on the observation that the calculation of the power either in the time domain or in the frequency domain doesn't really matter. The value is supposed to be the same. So the total power of a periodic signal is the sum of the power of the DC fundamental frequency and harmonics components in the frequency domain. And this is the calculation in the time domain. This equation, these two equations, supposed to be the same. Before we proceed to the next page, we want people to understand an extra concept, which is power spectrum. So the power spectrum of a periodic signal actually is the distribution of the squared magnitude or amplitude spectrum of the original signal. So that is the definition of the power spectrum of a periodic continuous time signal. So this is one example how we can make use of the Parseval law to help us calculate the power of a given periodic continuous time signal. So we can convert this signal from the time domain to the frequency domain. So this is the Fourier series. And we see there are three components. One is the DC components, the first harmonics and the second harmonics. And the power actually is the summation of the power of each terms in there. So the total power actually is 42. And if we do the calculation in the time domain, without any surprise, we see that the values are the same. And here is another example, show what is the meaning of the effective bandwidth for rectangle periodic signals. So we ask you to please calculate the power of all harmonics inside the effective bandwidth of a periodic rectangle signal shown in here, given the parameters, the specific numbers of the parameters. So what we need to do is, first, we probably need to figure out the power spectrum. So here is the spectrum. And if we do the square of the amplitude spectrum, we're going to get the power spectrum like that. And the effective bandwidth actually is the origin and the first cross-zero point. And what we can figure out is there will be 5 different harmonics. So the power inside the effective bandwidth actually is the summation of the power of DC components and the first 5 harmonic components. So based on this observation, we can calculate the power inside the effective bandwidth equal to 0.18. And what is the total power of the original rectangle signal? It's also straightforward. We can calculate the power in the time domain, and the result is quite straightforward, 0.2. And the percentage of the power inside the effective bandwidth versus the total power actually is equal to 90%. So that proves the power inside the effective bandwidth actually is a majority of the total power for any given periodic rectangle signal. To summarize the continuous time Fourier series, so we first introduce this more compact format of Fourier series. And we also introduce the continuous time Fourier series in this equation as the definition. And we also introduced that there are some characteristics of the spectrum in the frequency domain. And we also introduced the Gibbs phenomenon. That is, when we have a finite number of harmonics to synthesize the original signal, then at the discontinuity points, there will be some oscillation, and the overshot at the discontinuity will be 9%. And then next, we introduce the properties of continuous time Fourier series, and here are the list of those properties. Thank you.